Hello, I'm Erin, and I'm in Dr. Grimm's organic chemistry class in group 6, and I'm going to work this spectral problem for this molecule here, C7H14O2. And we're going to use infrared spectroscopy, carbon-13 nuclear magnetic resonance, and proton nuclear magnetic resonance. The first thing that we need to do is calculate the degrees of unsaturation for this molecule. So the way that we're going to do this is and there's several formulas, but we're going to multiply the number of carbons by 2 and add 2 to give us the number of hydrogens that would be typical of a saturated alkane. And then we're going to subtract the number of hydrogens that we have here in the formula. And we're going to simply ignore the oxygen, which can insert itself in between carbons, and then we'll divide that whole calculation by 2. So here we have 7 carbons times 2 plus 2 gives us 14 plus 2 is 16, minus 14 is 2, divided by 2 is 1 degree of unsaturation. And so what this tells us is that we are going to look for one double bond in this molecule, one degree of unsaturation. Let's start by looking at the information that we get from the infrared spectroscopy data. So we have several peaks here that are interesting. The first one with the largest wave number over here on the left of the graph, we have a couple of peaks here near 3,000, one at 2950 and one at 2850. These are typical for our CH stretches in alkanes. So we're looking at, definitely looking at an alkane and some alkane groups. And then we also have a very strong peak here at 1740, which is in the range and very significant for a carbonyl group, so a CO double bond stretch. Then we have a peak here, which is also typical in alkanes, around 1460, representing some of those HCH bends. And then we have several other peaks that are a bit more difficult to interpret, but we could guess that maybe this one here at 1200, around 1200, and this one around 1020. Those could be, those are in the range for the CO single bond stretches. And we know that we do have 2 oxygens in our molecule, so that is definitely a possibility. Could be looking at something like an ester at this point, with 1 carbonyl group and 1 CO single bond. So now we're going to look at the carbon-13 nuclear magnetic resonance data. And here we're going to first just count the peaks that we have. So we have 1, 2, 3, 4, 5, 6. And so what that tells us is 6 unique carbons in the molecule. Though from the molecular formula, we see that we have 7 total carbons. So we're going to be looking for a little bit of symmetry here, 2 carbons that are going to be essentially equivalent in this molecule. Okay. So the first peak over here on the left with a higher reading, a higher chemical shift at around 172. That's going to represent a, that's in the region above 80 for a trigonal planar carbon, so an sp2 hybridized carbon. And so this confirms that we probably have a carbonyl here, an sp2 carbon bonded to an oxygen. Okay. Now we're moving down here below 80 in the range of sp3 hybridized carbons, so tetrahedral carbons. And this first one with that's further downfield is probably bonded to a very electronegative atom. Now from our molecular formula, we see that our option for an electronegative atom is only oxygen. So we can suppose that this tetrahedral carbon is single bonded to an oxygen, which also confirms that this is probably an ester. Next, we have a peak around 43. This is still a bit downfield, and so this sp3 tetrahedral carbon is probably close to that carbonyl functional group. it's not very shielded. Some of the electron density is being taken by that, that carbonyl group. And then we have 3 more sp3 tetrahedral carbons that are more upfield and probably further away from that ester, from that carbonyl group. Now let's look at our proton nuclear magnetic resonance data for this molecule. We have, from the molecular formula, we see that we have 14 total hydrogen atoms. And this graph shows us 5 sets of peaks, 1, 2, 3, 4, and 5. Okay, so that means we have 5 unique types of hydrogen bonding environments. From when I measure these integrals just with a ruler in millimeters, I retrieve this data, 9 millimeters for these two, 4 millimeters on this one, 12 millimeters here, and 24 here. If I divide all of these just to get a smaller ratio by the smallest one, 4, I get a ratio of about 2 hydrogens here, 2 here. This is about, it's not exact, of course. 1 hydrogen here, 3 here, and 6 here. So that gives us this ratio, 2, 2, 1, 3, 6 hydrogens. And if we add up those numbers, they do equal 14, which is the number of hydrogens in our molecular formula. So this confirms that we're probably on the right track here with, the measurements are not exact, but it confirms that we're probably right, supposing that this represents 2 hydrogens in the molecule, 2, 1, 3, and 6. Now, if we analyze the chemical shifts here, we're going to need this n+1 rule, which means that we're going to take the number of neighboring hydrogens for the ones in question. So if we look at this first peak, we have, this is representing 2 hydrogens that are equivalent, and we're going to count the number of neighboring hydrogens and add 1 to give us the number of, for multiplicity here. So we have 1, 2, 3, 4. So this is a quartet. And what that means is that these 2 hydrogens have 3 neighbors. We're going to just subtract that +1, and that means that we have 3 neighbors. The 2 hydrogens that we get from the integration means that we're probably looking at a CH2 group. That is sp3 hybridized, so tetrahedral. We're below 5 parts per million. We're not even seeing up to 10 parts per million on this graph. So all of these hydrogens are in a tetrahedral sp3 hybridized carbon environment. Okay, so a CH2 group with 3 neighboring hydrogens. We're going to just do this same process for all of our reads here. So if we look at our next set of peaks, our integration gave us 2 hydrogens here. It's a doublet, so that means just 1 neighbor. So again, a CH2 group in an sp3 carbon environment with only 1 neighboring hydrogen. It's above 2 parts per million. So this could mean that this CH2 is carbonyl adjacent. I'm sorry, I forgot to mention that this one way downfield here at 4 in the sp3 range is going to be bonded to an electronegative atom because it is so far downfield in this sp3 carbon range. So that's going to be our sp3 carbon that is bonded to an oxygen. If we look at our next peak here, the integration gave us just 1 hydrogen. It's really hard to read how the coupling is here, but it looks like a septet to me, so 7 little peaks. And so that, because it's only 1 hydrogen, we're looking at probably a CH group, again in that sp3 carbon environment. And if it's a septet, that means it has 6 neighboring hydrogens. But we're going to put a question mark here because it is hard to read. So we'll hold off on being certain about that just yet. Next, we have a triplet here representing 3 hydrogens. So that means a CH3 group with two neighboring hydrogens. And because it is farther upfield, we're going to say this is probably farther away from any carbonyl or ester group. And then finally, we have this integral that's the largest one, representing 6 hydrogens. Now, of course, those can't all go on the same carbon, so we're probably looking at two CH3 groups that are equivalent. So there's our symmetry that we were looking for back from the carbon-13 nuclear magnetic resonance, where we saw there are only 6 unique carbons in this molecule, even though we have 7 total carbons. So there are symmetries probably right here on two equivalent CH3 groups. And those share, because this is a doublet, only one neighbor hydrogen. All right. So one more thing that this data can tell us, because we have 1, 2, 3, 4, 5 peaks. But we have, and then this one is probably representing 2 carbons, and the other one's 1 carbon. So that's still only 6 carbons, but we have 7 in our molecule. So that tells us that that carbonyl, trigonal planar carbon is probably not bonded to any hydrogens. It's probably bonded to another oxygen, making it an ester, and a carbon on the other side. So that's going to become more clear when we summarize all of this data, but just wanted to point that out. So let's look at a summary of all the data we've gathered so far. We're pretty sure now, both from that infrared spectroscopy and from the carbon-13 NMR, that we're looking at an ester. We saw here that we have a strong peak representing that carbonyl group and probably some CO stretches, and that was confirmed in the carbon-13 NMR with our reads at 172, which is right in the range for a trigonal planar carbon, double bonded to an oxygen, and this fairly downfield sp3 tetrahedral carbon, single bonded to an electronegative atom, which in this case is an oxygen. So we are likely looking at an ester here. And then this carbon, of course, which is fairly downfield as well in that sp3 range, is probably that carbonyl adjacent carbon. Okay, then if we bring that together with our chemical shift data from our HNMR, we see that we probably have a couple of neighbors here that can go together. This CH2 group has 3 neighbors, could be this CH3 here that has 2 neighbors. So that could be on one side of our ester. And then this CH group with 6 neighbors could be next to these 2 CH3 groups, which would be 6 hydrogens. And those 2 groups have only 1 neighbor, which could be this CH group here. But that leaves out our CH2 that has 1 neighbor. So where are we going to put this one? We have 2 sides of our ester already occupied. Well, remember we said that this septet, it was hard to interpret. So if it were not a septet, but a nonet, then that would mean that the CH group actually has 8 neighbors. And that would give us room to put this CH2 group on the other side, who of course has only 1 neighbor, being this CH group. Let's start putting the molecule together and we'll get an image of what this looks like. So we know we have a carbonyl group. We know we have an sp2 carbon, likely bonded to an oxygen, because remember there was 1 not represented in the HNMR data, not bonded to any hydrogens. So that means an oxygen on one side and a carbon on the other side. And that gives us this carbonyl here and this CO single bond read here. Here's that next carbon representing this CO single bond. All right, now let's put in our neighbors. We have this CH2 group with 3 neighbors and this CH3 group with 2 neighbors. So here they are. And then on our other side, we've now corrected this to a nonet. We're going to start with our CH2 that has just 1 neighbor, which is a CH group here, who has 8 neighbors, which are going to be these 6 hydrogen here, and these 2 here.